Okay, so last time I talked about just sort of like where this fits into mechanics and stuff. Now we're going to get into some mathy stuff related to this class, but we're going to start with just mathematical preliminaries. Um, I think I meant to. Did I assign some of the vector review for last time? Anybody have any questions about any of that? We answered some in dynamics, I guess. So you don't have any left. Okay. Um, okay. Well, I'll probably assign the rest of them today. Let me know if any questions come up. So now let's get into the mathematical preliminaries. And for this class, the key math that we're going to use all the time is matrix math. Um, so a matrix, usually the variables representing matrices are given capital letters, and they're indicated with like a undersquiggle like that. In textbooks, they're usually just given like bold typeface. So this is the matrix A, and let's say that it has the values 2, 1. I'm going to try to be consistent reading these off this semester and read across the rows, and then when a row is done, go down to the next row. So 2, 1, negative 2, 4, 0, 6. This is called a 3 by 2 matrix. So that tells you what the size is. The 3 refers to the number of rows, and the 2 refers to the number of columns. And when you're talking about individual elements in a matrix, people use the lowercase letter of the name of the matrix. So we'd say A11, and the order of the subscripts is the row number followed by the column number. So A11 would be 2. A12 would be 1. A21 would be negative 2. A22 is 4. A31 is 0, and A32 is 6. In this class, there are really just 4 matrix sizes we're going to deal with. The first one is any kind of vector. So I represent that like in the vector review. I represent vectors as a column matrix. So that'll be a 3 by 1 matrix, and that's any kind of vector in 3D. So for example, we would have a force vector that's equal to, let's say, 10,000, negative 15,000, and negative 5,000 with units of newtons. And the way that you see this stuff most of the time in physics, and for a lot of you, the way that you the way you talked about vectors in statics too. This is equivalent to 10,000 newtons I minus 15,000 newtons J minus 5,000 newtons K. So that's what it means. It's always the X component first, Y component second, Z component third. Okay. And I will also sometimes, I guess, if we're doing 2D problems, I might write something like negative 20,000, positive 2,000 newtons. And you can think of that as, that's just saying that if we're in the XY plane, this is negative 20,000, positive 2,000, and then 0 for Z. Okay. The second matrix type that we'll use is 6 by 1. And this will be the Voigt form of stress or strain. We'll use that form a lot of times, but not all the time. So for example, the Voigt strain will be something like 1.5 times 10 to the minus fifth, 0, 0, negative 6 times 10 to the negative 6, 1, 2, 3, 4, 0, 2 times 10 to the minus 6 or something. Okay, so that's an example of the strain at a point represented in a Voigt form. I'll talk about what, you don't know what you use Voigt for yet. You don't know what strain is yet. And we'll talk about all that. But this is how we'll use 6 by 1 matrices. We'll use 3 by 3 matrices. For two different things that we'll use a lot. The first one is stress tensors. And we'll also use these for rotation matrices. So a stress tensor would be something like, that's the Greek letter sigma. That's usually going to represent our stress tensors. It has the undersquiggle thing, so you know it's a matrix. And let's say, for this case, the values would be 6 times 10 to the 6, 0, negative 8 times 10 to the 7. This stress tensor has a property called symmetry, which means that for the things that aren't along the main diagonal, there has to be a mirroring effect across the diagonal. I'll talk about that in mathematically what that means in a second. 5 times 10 to the 7, negative 2 times 10 to the 6, negative 8 times 10 to the 7, negative 2 times 10 to the 6, and then negative 5 times 10 to the 7. And this has units of pascals. Pressure. It's not a pressure, but it has the same units. One thing to notice is in any engineering application, so this is a strain. And notice that those values are tiny. That's because engineering materials cannot deform very much before they get out of the range of deformations that are allowable in this class. And you don't have to know what strain means to just sort of understand kind of generally that if you take a steel bar, you need something really strong to do this. But if you take a steel bar and stretch it to twice its original length, long before that happens, it's going to break in two. And long before that happens, it's going to deform permanently. And once that permanent deformation happens, we're beyond the range that we can analyze with these methods. So deformations, strain is a measure of deformation, and deformations are going to have to be small in this class. This is a stress. And these are going to be huge values. And that's because, again, for engineering materials like steel is the one that we're going to talk about the most. In order to even have any reason to talk about deformation, you have to apply a lot of force per square inch to steel, you know. And so when we talk about stress, we're going to have big values. When we talk about strain, we're going to have small values. If you ever get those flipped, most likely you used the inverse of a matrix or something went wrong, okay? So in any problem, ask yourself, do I have small stresses? No. Do I have big stresses, small strains? That's not a guarantee. If you don't have that, it's not a guarantee something went wrong, but you want to think about it a little bit at least, you know. Um, and then the last one is a 6x6. I'm not going to write that out because it takes forever. But 6x6 matrix. There are two 6x6 matrices that we're going to use. Those are the stiffness and compliance matrices. Um, we're going to use the compliance matrix most often. But the stiffness matrix you can think of as a 3D version of the spring stiffness case K, the modulus of elasticity, or what do you call that? Young's modulus. No, you don't have a name for that, do you? Spring constant. Just call it the spring constant. Yeah. So it basically does the same thing. If you have big values in your 6x6 stiffness matrix, you have a material that's very hard to deform. If you have small values in your 6x6 stiffness matrix, you have a very flimsy material that's easy to deform, just like that value K. Um, and one thing, we'll get to this later, inverses and stuff, but the stiffness matrix is the inverse of the compliance matrix and vice versa. So that means that if your stiffness matrix values are big, your compliance matrix values are really small and vice versa. There are 3 ways to enter matrices into a TI calculator. Is there anybody here who doesn't use a TI calculator? Use a Hewlett-Packard or something? Okay. So, depending on what model you have, you know, you have to use different ways to enter matrices. Um, okay, so the first one, I think this is with the older the calculators that were sold earlier. Um, you have to go to you have to hit the matrix button, and then it gives you sort of like a GUI interface sort of thing for entering your matrix values. So go to matrix, go to edit, and then it asks you what the dimensions are. If you want 3 rows and 5 columns, then you enter 3 by 5, and then 1 by 1 just enter the things in. I believe this is what you have to do for a TI-83, an 84, and maybe an 86 also. And I think this also, this, I don't know, maybe that's all. The second way is square bracket and go, okay, so square bracket for the whole matrix, and then each row is in its own set of square brackets, and the elements along the row are separated by commas. So like 2, 1, -2, 4. Ooh, these are the same values I gave in my example matrix at the top. It's like foreshadowing. Okay, so 2, 1, -2, 4, and then 0, 6. Yeah, rows. Yep. And I think you can use this maybe not on 83s, maybe. You can on 84s and maybe on 86s. Yes, you can. You're right. Oh yeah, so that one's pretty flexible. And then the last one saves you a few keystrokes. Uh, I think might only be allowable on an 89, and that's square brackets for the outside, and then commas take you across the rows, and semicolons take you to the next column. Um, that's the one I'm used to because it just saves a little time. But and Inspire has its own way to do it. It's more like that first one, like you go into, like you tell it you want to enter a matrix and then fill in the values. Okay, so now I want to talk about a couple properties of matrices, some different types of matrices that we'll see, and then I'll talk about how to do, mostly what we're going to want to do is matrix multiplication, multiplying 2 different matrices. Um, okay, so the first thing is transpose. Um, there's a transpose for any matrix, no matter what its size is. That's not going to be true of all these things. Some of these calculations require matrices of certain shapes. And the way you do it is for every element, the original ijth element in the new jith element. So what you're doing is just switching the rows with the columns. Okay, so for example, if you have a matrix A that's equal to 1, 2, 3, 4, 5, 6, then the transpose of that matrix, we denote that A with, it looks like it has an exponent of capital T. It's not an exponent, it's just a symbol, saying it's an operation. So the first row of A is 1, 2. Now that's going to be the first column of A transpose. The second row of A is 3, 4. So that's going to be the second column of A transpose. And the third row of A is 5, 6. So that's going to be the third column of A transpose. I think all TI calculators have a built-in function for this. Before I go into that, so notice the transpose of an M by N matrix is an N by M matrix. Most TI calculators have a built-in transpose function. And it's called just, it looks like a small exponent, capital T. You just have to scroll through the list of functions to the T. By the way, so the lists of functions on all the calculators are done differently. Some of the earlier ones have specific vector functions, and that's where you find this, or matrix functions, I guess. I think the 89 just has a big list of all the functions, and you don't want to scroll all the way through all of them. So when you get to the big list of functions, hit the T button on your calculator, and it'll jump you to the T's, and then you can scroll from there. Catalog, I think, yeah. What do you have there, an 84? Or that's an 80? No, that's an 89, yeah. So if you go to catalog and then hit the T, I think it jumps you right to the transpose function. No, I think that's time. But if you hit that button so if you hit catalog and then hit that time button, I think it jumps you right to T. Okay. Now, one important matrix shape is a square matrix. And what would you guess would be the requirement for something to be a square matrix? It probably means just what you think. Exactly, same number of rows as columns. So for example, so let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. And every square matrix we can separate into diagonal elements and off diagonal elements. So for a square matrix, not for other types of matrices, so we can separate the elements into diagonal and off diagonal. The diagonal elements are the ones where the row number equals the row number equals the column number, or intuitively it's just these, the ones you would maybe think would be the diagonal, but intuitively you would think there are two diagonals, that one and this one. But notice, this is element 1, 1, 2, 2, 3, 3. And so those are the diagonal elements. These don't have that with the element numbers. That's 3, 1, 2, 2, and 1, 3. So that's not the same. Okay, so so the ones in red are the diagonal elements, and then the off diagonal are just all the other ones. And so these, I guess, to describe these, you'd say I is not equal to J. And all this stuff I'm doing with the I's and J's, and it has to be this and this. By the way, for the people who've taken computer science and enjoy like programming and stuff, you can imagine how all this stuff is pretty easily turned into an algorithm by just using for loops and zipping through all the I's and all the J's and putting, saying one thing has to happen if I is equal to J. This stuff is all pretty easy to code. And so if you have a calculator that doesn't, if I say there's a built-in function and you go and your calculator doesn't have a built-in function, bring it to office hours and we'll write a program for it in 5 minutes or something. Okay, so so I gave 4 matrix types that we're going to deal with in this class. Only one of those sizes is square, and that's the one for the stress tensor and rotation matrix. Okay, so stress tensors and rotation matrices are square matrices. The other ones are not. Oh, yep, you're right. The stiffness and compliance are too. Yep. Okay. A special case of square matrices. So this can only happen square matrices. Um, and this is called a symmetric matrix. Um, a matrix A is symmetric if A is equal to A transpose. Um, that means that, so in other words, for the off-diagonal elements, lowercase a I j is equal to lowercase a j I for every I and j. So for example, this is the one that I said it has to be kind of like a mirror image of itself across the diagonal. So let's say we have the matrix, 3 by 3 matrix, 1, 3, -1, 3, 5, -4, -1, -4, 3. So here is the main diagonal. And now for the off diagonal elements, that's equal to that. That's equal to that. And that's equal to that. Notice that if you have a symmetric matrix, not all of the elements are independent of each other. You know, I gave you the values for the diagonal, and then these 3 values, then these are fixed. Those can't be anything, you know. So symmetry takes the number of independent, mostly for us, we care about these 3 by 3 matrices. So for a 3 by 3 matrix, if it's symmetric, we don't have 9 independent values, we only have 6. Okay. So a symmetric 3 by 3 matrix only has 6 independent values. Where have we seen that number 6 before? Well, that Voigt form that I mentioned, we still don't know what stress and strain is, but um, the fact that there are only 6 independent values in a symmetric 3 by 3 matrix means that you can represent a symmetric 3 by 3 matrix in a Voigt form with only 6 values. And so that's the connection that we're going to have between these 3 by 3 matrices. So you can represent, by it I mean a symmetric 3 by 3 matrix, as a list of 6 values. And that's what the Voigt form is. Um, well, there's really 2 things I want you to remember. So let's make this number 1. So notice 2 things here. This is the first one. A symmetric 3 by 3 matrix you can just represent as a list of 6 values, and that's called Voigt form. And the second one is all eigenvalues of a symmetric matrix are real. Um, and we're going to see that when we haven't talked about how to do eigenvalues or anything like that, but we're going to use eigenvalues of these 3 by 3 matrices a lot. And the eigenvalues that we get are going to represent physical. So we're going to get eigenvalues of a stress tensor. The eigenvalues are going to be stresses that have a physical meaning. And so they need to be real for that to make sense. There's no such thing as imaginary stresses. And we know that they're always going to be real because the stress is a symmetric tensor. Okay. Anybody have any questions about anything yet? Yeah. A Voigt form? Yeah. So this, do I have? Yeah, let's do it for the one that. So the Voigt form of this. Yeah, so the way you do the Voigt form is you'd go, well, let me first write the pattern and then I'll write what it would be for this matrix. So if this is A, this is the matrix A, then the Voigt form would be the diagonal, A11, A22, A33. And then what do you think would be, like, if I asked everybody to guess how the off diagonal elements were entered, they'd all pick the same order. There's no reason it has to be that, but everyone would say, okay, well, let's go 1, 2, 1, 3, 2, 3, every single person. And so whoever designed Voigt form was like, I'm going to do it backwards of that. And they were the first one they got to choose. So I don't know. There could be a mathematical reason for it, but the off diagonal elements are exactly opposite of what you would think. It's A23, A13, A12. And that's literally how I remember the order of it. I'm like, I think about what makes sense and then I do the opposite of that. So for this case, so that's 1, 5, 3, and then -4, -1, 3. Any other questions yet? Okay, so now matrix multiplication. So you can think of matrix multiplication as a series of dot products. So remember the dot product? It's not a series, I guess it's a sequence, really, technically. So remember, if you're taking the dot product of 2, 1, -2, and -5, 0, 6, that's equal to 2 times -5 plus 1 times 0 plus -2 times 6. In this case, that's -22, I think. Yeah. Okay, well, if you're multiplying, so let's say we're multiplying two 3x3 matrices. The first one is 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're multiplying that by, just keep this going, 10, 11, 12, 13, 14, 15, 16, 17, 18. Then what you're going to keep doing is you're going to take dot products of the rows of the left matrix. So a row of the left matrix with a column of the right matrix. And that dot product goes in the element row. So let's say that the row of the left matrix we're going to call I. Okay? And the column of the right matrix we're going to call J. Okay? Then the result, that dot product goes in the element IJ. Okay, so so we'll first start by taking the dot product of this with this. Okay, what's I? What's the 1 and what's J? 1. So this is going to go in element, the dot product of these two is going to go in element 1, 1. Okay, so take that dot product and I think you get 84. I'm definitely not doing that in my head. I have it written here. Okay, and now we'll go dot product of this with this. Yeah, so 1 times 11, 2 times 14, 3 times 17. Yep. So what's I in this case? 1. What's J? 2. So that's going to go in the next thing over, and I get 90 for that. I'm not going to do this for all 9 values, but one more, and then I'll just view the rest of them. So now we'll go 1, 2, 3, added with 12, 15, 18, and you get 96. Actually, I'll do one more so you can see what happens when you change the row, but it just keeps following this pattern. So now we'll take the dot product of the second row of the left matrix with the first column of the right matrix. I is 2, j is 1, so this dot product goes in the 2, 1 element. You get 201. And just keep going like that. And if you keep going with this, like you can try this later or whatever to make sure it makes sense to you. You get, so that's 216, 231, 318, 342, 366. And in every TI calculator, you just use the regular multiplication button and it'll multiply the matrices for you. So you'll never in this class have to do it by hand like this. Just enter them into the calculator, use the multiplication button, and it'll do this. Okay. Okay, so a couple more things to notice about this in general. So first, to multiply any matrices, the number of columns of the left matrix must equal the number of rows of the right matrix. That's because when you take these dot products, you can only take dot products of vectors that have the same length, you know. So if we were dealing with a matrix that had 4 rows, and, that had 4 columns, I think I wrote it right, I just said it wrong. 4 columns here and 3 rows here, then that dot product doesn't make sense, so you can't do that multiplication. It depends on the application, but usually not. I mean, I've never seen it where you could, but I'm sure there's some, matrices can stand for all sorts of things. So there's probably some way that could happen. And so we also, using this idea, can figure out what the size of the output matrix is going to be if the left matrix is M by I, M rows and I columns, and the right matrix is I by N. That's those I's have to be the same so that we can multiply these. then the result of multiplying them together is m by n. So if you're multiplying two 3 by 3 matrices, the output is 3 by 3. That's what we're going to do most of the time. Two more quick things, and then we're out of here. Number 2, order matters in matrix multiplication. This is one case where multiplying matrices is different than multiplying numbers, you know. So A times B is not equal to B times A. It's not commutative, right? Commutative, right? And then the last thing is order matters, but grouping doesn't matter if you're multiplying more than 2 matrices. So grouping doesn't matter for greater than 2 matrices. So it is associative, right? Tell me if I'm wrong. So A times B times C is equal to A times B times C. Okay, but you can't flip any of the orders. Any questions about that? Okay, see you Friday.